There is an additional class of problems that we're going to encounter in the course, and that with a little bit more thinking, we can learn how to solve based on what we have learned so far. These problems look like follow, which is maximize an objective function, for example, a profit function for a firm, subject to two constraints, which is the control variable x has to be at least greater than a lower bound L and at most an upper bound B. So it has a lower bound and an upper bound. And for simplicity, because this covers most of the cases that we're going to see, the problem satisfies some version of the concavity constraint. So we're going to assume that the second derivative of this objective function is less or equal than 0. So an example of this will be a firm that has a profit T of x is the profit as a function of the level of production, the quantity produced, and the total profit is P of x, the quantity produced, times the price at which it sells, minus the cost of production as a function of the amount produced. As we have seen under the concavity conditions, this profit function satisfies that the second derivative is less than 0. And the key idea is that before any level of production greater than 0 that's feasible, so we were maximizing over the entire x range, but now we're going to look at problems in which maybe for some reason that we will encounter before, say a government policy restriction, x needs to be between the ranges L and capital B. It cannot go below there. It cannot go above there. It has to be restricted to this area. Now, in this version of the problem, there are three cases that we have to worry about. Two of them involve corner solutions. One of them involves an interior solution. Let's look at each of them in turn. So consider first the case with a corner solution in which the optimal thing to do is the lower bound. That's a case that looks like follows. You have x, you have the range over which you can choose, which is L and B. Let's draw that here. And when you plot the marginal function for the total payoff, it looks something like this, let's say. It is decreasing because the second derivative is less than 0, but the key thing is that at the lower possible bound, it is already negative. In this particular case, it doesn't pay to even take the lowest level of production, which in case is x equals L, because producing that additional level will decrease the total payoff by this much. And any subsequent unit of production will decrease the payoff, but even more. Therefore, the unique optimal solution in this case is to set x stars equal to the lower bound. Now consider the other corner solution that entails actually producing at the upper bound. This is a case that looks as follows. You have, again, the problem with the bounds at L and at B. Remember, this is the range over which you can produce. And it's a case in which the marginal total payoff function looks, let's say, something like this, which has the property, the key property, that at the up is always above 0, and especially at the upper bound, it is still above 0. It is easy to see in this case that the unique optimal thing to do is to produce at the upper bound. Why? Because every single unit of production has a marginal total payoff, which means that it increases the total payoff. So you should keep doing it until you reach the boundary. And in fact, if you had not encountered the boundary, if the boundary had not been there, you would like to keep going. But that is not possible because there is an upper boundary to what you can produce. So in this part, in cases that look like this, the unique solution is a corner solution that entails producing the upper boundary. Now consider the case that leads to an interior solution. This is a case that looks like follows. As before, we have the range over which can produce the control action, let's say between the lower and the upper bound. And the key property of the case is that if you look at the marginal total payoff, it looks like this. It is decreasing because of the second derivative being less than 0, but it crosses 0 between the lower and the upper bound. Now, I claim that it's easy to see that in this case, the unique optimal solution is this point, which is given by the solution to this equation. And the reason is the follows. Suppose that you start at the lower bound. Producing the first unit generates a return. It increases the total payoff by this much. The same is true for every additional unit until you reach this point. After that, producing an additional unit has a negative impact in your payoff because the marginal total payoff function is negative. So this is the best thing that you can do. Now, the logic that we have just developed is so useful in many economic examples that it's worth highlighting it as another key result. And the result states the following, just to be succinct on what we have learned in this last video. Consider the problem, maximize an objective function over a control variable x with the restriction that x has to be above a lower bound L and below an upper bound U. And assume that the problem satisfies the concavity properties so that the second derivative of the objective function is less than 0. Then we know there exists a global maximum and that it falls in one of these three cases. A first corner case in which the solution is a lower boundary, and that happens when the marginal value of the objective function at the lower boundary is less than 0. A corner solution number 2, which is the unique solution is to move to the upper bound and do only that. That happens when the marginal value of the objective function at the upper boundary is greater than 0, and an interior solution that happens for all of the cases in between, in which the solution x star is given by the solution to this equation.